Between Eastern Europe and Western Asia lies a sea whose name seems to describe a vast expanse of dark water. Yet its waves can appear blue, green, turquoise, and even whitish from space. The true mystery remains hidden beneath the surface. In a deep world where oxygen is virtually non-existent, toxic gases accumulate, and ancient ships can be preserved for thousands of years. The Black Sea didn't get its name because its waters are black. Its identity arose from a combination of history, geography, navigation, chemistry, and legends that still raise questions. The Black Sea occupies a nearly enclosed basin of over 430,000 square kilometers, connected to the Mediterranean Sea by a series of narrow straits. The Bosporus carries its waters to the Sea of Marmara, the Dardanelles open the way to the Aegean Sea, and finally, the system connects to the Mediterranean. Turkey, Bulgaria, Romania, Ukraine, Russia, and Georgia border it. Large rivers such as the Danube, the Dnieper, and the Don carry enormous quantities of fresh water, sediment, and nutrients into its interior. This river inflow reduces surface salinity and contributes to a vertical structure very different from that observed in most seas. To the naked eye, its water does not appear permanently dark. Near the coast, it can take on brownish tones due to sediment. In open areas, it is usually a deep blue. During certain microbial blooms, it displays turquoise colors that stand out even in satellite images. The name, therefore, represents a historical and cultural label, while the true character of the sea lies in its inner layers. There begins one of the most extraordinary oceanographic anomalies on the planet. A surface teeming with oxygen and organisms remains separated from a vast mass of deep water laden with hydrogen sulfide. The boundary between these two worlds transforms the Black Sea into a natural laboratory capable of revealing how some of Earth's ancient oceans may have functioned. The simplest explanation states that the Black Sea received its name from the dark appearance of its waters. This interpretation is appealing, though it presents an obvious difficulty. The color of the sea constantly changes and rarely acquires a truly black hue. Geographical names often survive for centuries, while their original meanings are transformed, translated, or blended with new traditions. The Black Sea has received different names throughout history. Some ancient peoples associated it with dangers, storms, and treacherous coastlines. Others used words linked to cardinal directions, unknown territories, or symbolic characteristics. The ancient Greeks initially employed a name that is usually translated as inhospitable sea. Their navigators faced a space surrounded by unknown peoples, with few safe harbors in some regions and storms capable of developing rapidly. Later, as trade routes increased and Greek colonies arose on its shores, a more favorable expression, the hospitable sea, began to spread. Even those Greek names don't directly explain the modern term. The expression Black Sea appeared more clearly in later traditions, especially during the Middle Ages. Its exact origin remains debated because the words could have traveled between Persian, Turkic, Slavic, and Mediterranean languages. One of the best-known theories relates to an ancient symbolic system that assigned colors to the cardinal directions. In certain Asian cultures, black represented north, red was associated with south, white with west, and other colors could indicate east. From this perspective, Black Sea would have simply meant North Sea to the peoples located south of the basin. The name Red Sea has sometimes been used as a possible example of this geographical tradition. However, the equivalences varied between cultures and periods, so this interpretation remains a hypothesis and not a definitive solution. Another possibility stems from navigation. Storms can transform the surface of the Black Sea into a very dark grey expanse. Its basin generates short, abrupt waves, especially dangerous for ancient vessels. Under overcast skies, the water reflects the clouds and takes on an almost metallic appearance. From a wooden ship, without modern instruments and with a distant coastline, that landscape could appear threatening. The darkness could also have been associated with the depths. Sailors observed that certain metal objects retrieved from the seabed appeared blackened. In oxygen-poor environments rich in sulfur compounds, dark-colored metallic sulfides can form. An anchor or chain submerged for a sufficient time could return covered in a black layer. This phenomenon likely fueled tales of a poisonous and gloomy seabed, although it is difficult to prove that it originated the name. Coastal waters also exhibit variable visibility. Large rivers discharge clay, organic matter, nutrients, and microscopic particles. After heavy rains, a coastal strip can turn brown, dark green, or grey. Storms stir up sediment from the shallow bottom and further reduce transparency. Someone who knew the sea primarily from a port or estuary would have a different visual impression than someone who observed it from the open ocean. Therefore, the term black seems to encompass several layers of meaning. It can reflect a geographical location, a linguistic tradition, the perceived danger of storms, the darkness of some coastal waters, or the blackening of submerged objects. No single explanation has completely eliminated the others. The name functions as a historical time capsule. It preserves the memory of navigators who ventured into a nearly enclosed basin, surrounded by mountains, steppes, and territories that for centuries marked borders between empires. Its literal meaning eventually prevailed in numerous modern languages, although the water never needed to be black to justify it. Pure water has a slight bluish tint because it absorbs different wavelengths of light unevenly. Reddish colors are lost more quickly as they penetrate the water, while some of the blue light travels further and returns to the surface. The observed color also depends on the sky, the angle of the sun, the depth, the waves, and the suspended or dissolved substances. The Black Sea contains a particularly variable mixture. Rivers carry mineral sediments and organic matter from a vast drainage basin. Phytoplankton adds pigments. Particles scatter solar radiation. Dissolved organic substances strongly absorb certain colors. The result varies between seasons and regions. Out at sea under clear skies, the surface can appear dark blue. This color occurs when the water contains relatively few particles near the surface and absorbs much of the radiation that penetrates it. The depth of the basin intensifies the visual sensation, although the human eye primarily perceives the light returning from the upper layers. Near river mouths, other hues predominate. The Danube, for example, deposits fresh water, minerals, organic matter, and nutrients in its western sector. Suspended particles scatter light and can produce green, yellowish, or brownish colors. Currents carry these plumes of water, creating visible boundaries between bodies of water. Green often appears when phytoplankton concentrations increase. These microscopic organisms contain pigments like chlorophyll, which absorb certain parts of the spectrum and modify reflected light. A large bloom can transform vast surface areas. Some of the most striking images show the Black Sea covered in turquoise swirls. This phenomenon is frequently associated with coccolithophore blooms, single-celled organisms protected by small plates of calcium carbonate. The plates scatter light very effectively, creating a milky or pale blue appearance. From a ship, the bloom can look like a pale film spread across the water. From a satellite, the currents and eddies organize the color into gigantic spirals. The effect demonstrates the extent to which biology can transform the appearance of a sea without changing its name. Chlorophyll concentration, non-algal particles, and dissolved organic matter determine much of the basin's optical properties. For this reason, measuring its color from space allows scientists to estimate biological productivity, track river discharges, and study current movement. Satellites don't simply observe a blue surface. They record minute differences in reflected radiation and transform them into maps of invisible processes. The waves add another variable. Each wave modifies the angle at which the surface reflects the sky. A choppy area mixes bright flashes, shadows, and white foam. Under dense clouds, the reflection takes on grey tones. At dawn or dusk, the surface can incorporate reddish and golden colors. The same body of water can appear blue from one direction and almost black from another. This illusion depends on contrast, lighting, and the inability of light to return from a certain depth. A dark surface reflects little visible radiation toward the observer, but that doesn't mean the liquid contains a black pigment. The phenomenon is comparable to a window. During the day, a pane of glass can reflect the outside. At night, the same pane appears dark because behind it is an unlit room. The sea also changes depending on the amount of available light and the substances the radiation encounters before returning. In deep water, sunlight weakens until it disappears. First, the reds are lost, then the oranges, yellows, and greens. Finally, a fraction of blue light remains, which is also absorbed. At several hundred meters, complete darkness reigns, but that condition applies to almost all deep oceans. The Black Sea's uniqueness arises from what accompanies that darkness. The Black Sea functions like two aquatic worlds stacked one on top of the other. The surface layer receives oxygen from the atmosphere and supports most marine life. Below lies a much larger mass of water without free oxygen, where chemical processes controlled by anaerobic microorganisms dominate. This separation begins with salinity. Rivers deliver abundant fresh water to the surface. At the same time, the Mediterranean Sea brings saltier water through the Bosporus. Due to its greater density, this saline current flows along the bottom of the strait and descends into the depths of the Black Sea. Near the surface, the opposite movement occurs. Less saline water flows out into the Sea of Marmara. Thus, the Bosporus contains two overlapping currents traveling in opposite directions. The upper layer carries water from the Black Sea outward. The lower layer carries Mediterranean water inward. The difference in density keeps the masses separate. In an open ocean, wind, currents, and temperature changes can mix large volumes of water. In the Black Sea, the salty layer at the bottom is too dense to rise easily. The lighter surface water remains on top. Between the two layers, a transition zone forms, acting as a barrier. Scientists describe this state using the concept of stratification. Each layer has different properties, and vertical exchange occurs slowly. Atmospheric oxygen only reaches the upper region. When organic matter dies and sinks, bacteria begin to decompose it and consume the available oxygen. As depth increases, the oxygen concentration decreases. Eventually, a suboxic zone appears where very little oxygen remains. Below this lies the anoxic zone, a vast region devoid of molecular oxygen usable by fish and most complex organisms. More than 80% of the volume of the deep basin remains in anoxic conditions. The exact depth of this boundary varies depending on the region and oceanographic conditions, but it is usually located approximately between 100 and 200 meters. Below this depth, the sea adopts a radically different chemistry. This structure makes the Black Sea the largest anoxic marine basin on the planet. At the surface, ships navigate, fish live, and photosynthetic organisms thrive. A few hundred meters below, an environment begins that is incompatible with almost all known marine fauna. The division remains invisible from the surface. A sunny beach may feature clear water, seabirds, and fishing activity. Beneath this landscape lies a deep body of water that has been isolated from direct contact with the atmosphere for centuries. The almost enclosed nature of the basin favors this situation. Exchange with the Mediterranean occurs through narrow, shallow channels compared to the great central depths. The deepest point exceeds 2,000 meters. Complete renewal of these waters is extremely slow. The Black Sea is classified as a meromictic basin, a term used for bodies of water whose deep layers remain separated from the upper layers for extended periods. A similar phenomenon occurs in many meromictic lakes, although the scale of the Black Sea is exceptional. The chemical boundary is also not perfectly horizontal. Currents, eddies, and seasonal variations displace the layers. During winter, cooling promotes some mixing in the upper region and contributes to the formation of a cold intermediate layer. However, this ventilation reaches a limited depth and does not transform the immense anoxic reservoir. This stability explains why the Black Sea appears ordinary from the surface and extraordinary when studied vertically. Its main mystery is colorless. It consists of a physical separation capable of maintaining two opposing environments within the same basin. When oxygen disappears, the decomposition of organic matter continues through different chemical pathways. Some microorganisms use sulfate, a substance abundant in salt water, to obtain energy. This process generates hydrogen sulfide, a toxic gas known for its characteristic rotten egg smell. In the depths of the Black Sea, this compound is dissolved in the water. Its concentration increases toward the bottom, creating one of the world's largest natural hydrogen sulfide deposits. Production is primarily related to the activity of sulfate-reducing bacteria acting on the submerged organic matter. Hydrogen sulfide is dangerous for oxygen-dependent organisms. It interferes with fundamental cellular processes and can cause death at high concentrations. For this reason, fish, mollusks, and most animals are confined to the upper, oxygenated layers. The depths, on the other hand, harbor microbial communities adapted to the absence of oxygen. Some produce sulfide. Others consume it as it rises toward the chemical boundary. In this intermediate zone, a complex network of reactions develops, preventing large quantities from reaching the surface. The gas remains dissolved due to pressure, the stability of the layers, and the action of microorganisms. The image of a huge, toxic bubble ready to burst is misleading. The sulfide is distributed within a gigantic body of water, and its arrival at the surface would require a profound alteration of the stratification. Even so, its presence fueled numerous speculations. Scenarios related to earthquakes, submarine landslides, warming, asteroid impacts, or extreme changes in circulation have been proposed. Some models explore what would happen if a disturbance suddenly released the gas. These analyses represent scientific exercises on unlikely risks and are not proof of an imminent catastrophe. The most frequent comparison is with Lake Nyos in Cameroon. In 1986, a sudden release of carbon dioxide from its depths formed a suffocating cloud that caused a tragedy in nearby communities. However, Lake Nyos and the Black Sea have different dimensions, gases, mechanisms, and structures. The analogy allows us to understand certain physical processes, but it doesn't establish that both systems will behave in the same way. Hydrogen sulfide also reacts with metals and can form dark compounds. Iron, for example, participates in reactions that generate black sulfides. This process offers a possible connection between anoxic depths and earlier observations of blackened objects. The true blackness of the sea, therefore, lies in certain sediments and chemicals, not in the overall color of the water. Partially preserved organic matter accumulates at the bottom. The lack of burrowing animals reduces the disturbance of some sedimentary layers. Sulfur compounds react with minerals and contribute to creating dark deposits. If a deep sample is exposed to air, its chemistry begins to change. Sulfide oxidizes and produces other substances. The smell may be intense, but the sample does not necessarily turn black. The word black simplifies a much more complex system of invisible reactions. The anoxic zone also serves as a window into Earth's distant past. For extensive geological periods, large oceanic regions had low oxygen levels and high concentrations of sulfur compounds. Studying the Black Sea allows us to analyze how carbon, nitrogen, iron, and sulfur circulate under similar conditions. The microscopic life in its depths demonstrates that a lack of oxygen does not equate to a complete absence of biological activity. Bacteria and archaea utilize substances that would be toxic to animals and sustain entire chemical cycles in the darkness. The bottom water appears motionless, though it actually participates in slow exchanges. Mediterranean water entering through the Bosporus carries salt and gradually modifies the deep water mass. Microbial reactions transform compounds. Particles sink. Nutrients can return to the surface through diffusion and limited mixing. All of this happens at speeds difficult to perceive on a human timescale. The surface changes with the seasons and storms. The depths retain conditions developed over centuries. This temporal difference reinforces the impression that there are two overlapping seas, one fast-moving, luminous, and biologically active, the other slow, dark, and dominated by sulfur chemistry. The absence of oxygen produces an unexpected consequence. Organic remains can be better preserved than in other marine environments. In an oxygenated ocean, bacteria, worms, mollusks, and specialized organisms decompose wood. Some species bore into ship hulls until they are destroyed. In the anoxic zone of the Black Sea, many of these decomposers cannot survive. A sunken ship that reaches sufficient depth enters a cold, dark, and chemically hostile environment for the organisms that would normally consume its structure. Archaeological expeditions have located extraordinarily well-preserved shipwrecks. Some retain masts, oars, rudders, ropes, and construction details that usually disappear elsewhere. This preservation transforms the seabed into an archive of ancient navigation. One of the most remarkable finds was a Greek merchant ship approximately 2,400 years old, discovered at a depth of over 2,000 meters. Its shape resembled vessels depicted on ancient pottery, but a complete example in such condition had never been found before. The ship remained protected because the wood was out of reach of most destructive marine organisms. The darkness prevented photosynthesis. The temperature remained relatively stable. The absence of oxygen slowed down numerous degradation processes. The basin also contains the remains of Roman, Byzantine, Ottoman, and more recent vessels. Each shipwreck represents a snapshot of the naval technology of its time. Hull shapes, joining systems, cargo arrangements, and personal belongings offer insights into trade, warfare, and daily life. The seabed also preserves ancient coastal landscapes. During the Ice Age, the global sea level dropped because enormous quantities of water were trapped in ice sheets. Coastlines shifted, and some now submerged regions became land. When the ice melted, the level rose again. This process fueled one of the best-known theories about the Black Sea, the hypothesis of a catastrophic flood that occurred when Mediterranean waters surged through the Bosporus area and filled a lower-lying basin. The most dramatic version imagined a massive waterfall surging northward, inundating inhabited territories and leaving its mark on the flood narratives of ancient civilizations. The idea gained popularity because it seemed to connect geology, archaeology, and mythology. However, the magnitude and speed of the event remain debated. Several studies suggest that the connection with the Mediterranean may have developed more gradually, that earlier exchanges occurred, or that water flowed from the Black Sea outwards during part of the period under consideration. A scientific review of the evidence published between 1997 and 2021 concluded that the persistent flow into the Mediterranean contradicts the version of a sudden flood comparable to the story of Noah. The influx of salt water did transform the basin. Before acquiring its modern conditions, the Black Sea went through stages in which it behaved like a lake or a low salinity environment. The marine connection allowed denser Mediterranean water to penetrate the seabed. This reorganization contributed to the establishment of stratification. Organic matter continued to sink, deep-sea oxygen was depleted, and bacteria began to produce hydrogen sulfide. This gave rise to the chemical system that currently preserves ancient ships and limits animal life in the deep sea. The supposed flood remains within the realm of scientific mystery because its reconstruction depends on sediments, microscopic fossils, ancient coastlines, and geological models. Each new core extracted from the seabed can provide dates, salinity changes, and environmental cues, but it can also complicate previous interpretations. The Black Sea contains a history written in layers. Recent sediments rest on the seabed. Below them are deposits accumulated during different climatic conditions. Further down are traces of periods when the basin was connected to or isolated from other seas. Its name might suggest darkness, but its true scientific value stems from its ability to preserve information. The oxygen-free depths function like a submerged library. Shipwrecks are its most spectacular objects, although fossilized microorganisms, pollen, shells, and the chemicals in the sediments tell a much broader story. The Black Sea's fame also stemmed from its surface. Its geographical location favors rapid weather changes, especially during autumn and winter. Cold air from the north can advance over relatively warmer waters, intensifying instability, wind, and swell. Early ships lacked engines, radar, and accurate forecasts. A sudden storm could drive them against rocky shores or away from harbors. Short, chaotic swells were especially dangerous for small, heavily laden vessels. This experience helped solidify the image of a harsh sea. Dense clouds transformed its appearance. The water reflected a gray sky, the waves blocked the light, and the foam stood out against a dark surface. From a ship's deck, the color could approach black for several hours. This occasional glimpse eventually became intertwined with its enduring name. The coastlines also offered landscapes capable of fueling haunting tales. In some areas, cliffs, fog, and the mouths of large rivers reduced visibility. Sailors could encounter floating logs, sediment, and currents that were difficult to interpret. Each shipwreck reinforced the reputation of a hostile environment. Added to this was the enormous cultural diversity of its shores. Greeks, Scythians, Persians, Romans, Byzantines, Genoese, Ottomans, Slavs, and peoples from the Caucasus sailed or traded in the region. Each civilization contributed its own names, maps, and stories. The result was an identity formed in layers, much like its waters. Black could represent the north, danger, depth, storms, or the unknown. The name survived because it encompassed many possible interpretations without relying on a single explanation. The Black Sea's surface layer supports fisheries, ports, coastal cities, and vital ecosystems. Its equilibrium depends on a relatively thin layer of oxygenated water. This characteristic increases its sensitivity to pollution and excess nutrients. During the 20th century, rivers carried large quantities of fertilizers, urban waste, and industrial byproducts. Nitrogen and phosphorus stimulated excessive algal growth. When these blooms died, the organic matter sank and its decomposition consumed oxygen. This process, known as eutrophication, particularly affected the northwestern sector where major rivers flow into the sea. Some coastal regions experienced episodes of hypoxia, organism mortality, and reduced water clarity. The introduction of invasive species also transformed the food chain. One of the best-known cases was the spread of a gelatinous organism native to the western Atlantic, capable of consuming large quantities of plankton and fish eggs. Its proliferation contributed to the decline of certain fish stocks. Subsequently, environmental control measures, changes in fertilizer use, and economic transformations reduced some of the pressure. Some indicators showed recovery, although the system remains exposed to pollution, coastal urbanization, shipping, and climate change. Warming alters surface temperature and can reinforce stratification. A more stable separation between layers hinders the downward transport of oxygen. At the same time, changes in rainfall and river flow alter the amount of fresh water and nutrients entering the basin. The boundary between the oxygenated and anoxic zones is one of the most closely monitored points. An upward shift would reduce the space available for fish and other organisms. Its position depends on a combination of circulation, biological productivity, and oxygen consumption. The main environmental risk is not that all the deep sulfide will suddenly reach the surface. The more realistic threat lies in the gradual changes that compress the habitable ecosystem and degrade coastal waters. The Black Sea seems to conceal a contradiction. Its water can be blue, green, or turquoise, while its name insists on a darkness that rarely appears literally. The contradiction disappears when color, name, and structure are separated. The visible color belongs to the surface and responds to light, sediments, plankton, and the state of the sky. The name belongs to history and preserves ancient geographical systems, navigational experiences, and cultural associations. The true darkness begins much deeper. There, light disappears, oxygen is depleted, and hydrogen sulfide dominates the chemistry. This region occupies most of the basin's volume, though it remains invisible to those observing from the shore. For this reason, the name seems both misleading and, at the same time, strangely appropriate. The surface water lacks permanent blackness, but the interior contains one of the most extensive dark and anoxic environments on the planet. Modern science has replaced many legends with precise measurements, although several questions remain unanswered. The exact origin of the name is still subject to debate. The story of its connection to the Mediterranean continues to generate different interpretations. The future evolution of its layers will depend on climatic and human changes that are difficult to project with absolute certainty. The Black Sea also preserves an extraordinary archaeological archive. Its depths protect ancient vessels, organic remains, and sediments capable of revealing changes that occurred over thousands of years. The same chemistry that eliminates almost all animal life from the seabed allows for the preservation of fragments of vanished civilizations.